Today we are going to discuss about the star and delta connections, what we have discussed in the previous session. Fine, so I'm sharing the screen right now. So whatever we discussed till yesterday, any doubt if you have, you can raise, otherwise we can continue with this solution, star connection and delta connection.
Sir, I wanted to ask you something.
Yes.
Sir, it is not based on study, but I wanted to ask you that we got a mail today on additional exam. So, is it compulsory for all, or it is for those only who are not given class tests of this December and January month?
Today I'm going to confirm, and then tomorrow in the morning I will let you know. Okay.
Okay, sir.
Fine. I will confirm it today, and then we will discuss. Okay.
And we also got the mail for the LPW examinations.
Yes. Examinations are there. Fine. So we have a very less time to complete the syllabus. So today, let me start this.
So it's finals that we are going to have our examination offline.
Yes. Today, as per the today's circular, it is offline. Fine.
Okay, sir. Thank you, sir.
Okay. So we have discussed yesterday two different things. One is star connection and another is delta connection. Right. So for star, we have seen that VL is equal to root 3 VPH and IL is equal to IPH. Clear. And similarly, for delta connection, it is reversed. So VL is equal to VPH and IL is equal to root 3. Clear. So based on this, we can have derivation of all these equations. We can derive and we can prove that these are equations for star and as well as for delta. Fine. Okay. So based on the connections, this is a star connection where ER is your phase voltage, and IR, which is flowing through this load. It may be inductor, it may be a resistor, it may be a capacitor. Fine. So this is your phase current. Fine. So this voltage is always between neutral and your line, and line voltage is represented like this. So here in this case, we can have a phasor diagram of the star connection where if the load is inductive, suppose if there is an inductive load is connected here, clear? Then we can represent these three different voltages. So ER is what? EPH or VPH. I'm going to write all these things here again repeatedly because ER, EPH, VPH are similar. So this is ER, fine. Because there is a neutral, this is a neutral, and the voltage between these two is your ER. So here we can draw a phasor diagram, ER, EY, and E, RY and B. So this is B. And according to that, ER, EY, and B, these are at 120 degree apart from each other. Are you agree with me? Agree
Yes,
with
sir.
me? Okay, fine. Now, as per the inductive load, we know that there is a current and voltage having 90 degree. Clear? But this inductor having a least amount of resistance also. So we can consider it as not pure inductor, but it may be a kind of mixture of resistor as well as resistance as well as inductance. Fine. So it may be considered that the angle which varies I and V, that is phi. So here the current vector IR, because IR is same phase current and line current, so IR can be represented with the help of this with an angle phi here instead of 90 degree. Similarly for EY, because these currents are in lagging in position, we are always considering in the anti-clockwise direction. Clear? So in anti-clockwise direction, this voltage is, which voltage is? Phase voltages. And similarly, you can consider this current as phase current or line current in case of star connection. In case of star connection. Is that clear? So this phasor diagram can be drawn for this star connection. Yes or no? Yes or no? Students, understood what I mean to say? Okay, fine. Now, similarly here, the same vector diagram is extended from the previous diagram. So here in the previous diagram, we know that ER was there, EY was there, and EB was there. Fine. So here I may represent with this diagram R. So this is your R phase. This is your R phase. Fine. Then Y. This is your Y phase, and this is your U phase. This is a W phase. Fine. So similarly, we have, because we know that for line voltage and line current, VL is equal to VP. I mean, sorry, IL is equal to IPH. Here, that is what. So we are not going to consider the current right now here in this vector waveform, but we can have three different voltage. Which voltage? Phase voltage. Phase voltage, and these are the phase voltages. So this is phase voltage VPH, or it may be ER as per this is. So this is voltage vector. Okay. Now here, if you want to find out the line voltage between R and Y, so here it is EY. So ER and EY. So ER and EY. Fine. So here this is a line voltage. Clear? Now from this diagram, here three vectors, ER is extended in the negative side. Similarly, this EB vector, which is extended in the opposite direction, minus EB. And similarly here, this EY vector is extended in the negative direction here. Fine. So here, the vector sum of these two, minus EB and EY, is your VYB. How it is? Let us see. Suppose if this is your diagram of star connection. Clear? So if it is, this is ER, this is EY, and this is EB. Fine. So if you extend this EB into the reversed side, or the line voltage between these two, EY and EB. So if you extend these two lines, there will be a voltage that is called VBY or VL, line voltage. So VBY can be observed with the help of this EY, phase voltage, plus vector sum of this EB. Clear? So with the help of these two different phase voltages, if we add together, then the summation or the resultant will be your VYB. So this VYB is your line voltage. Clear? Agreed with me? Agreed?
Yes, sir.
Okay, fine. So here, can we write an expression of VYB? is equal to EY plus minus EB. Can we write it for VRY also? VRY is equal to ER plus minus EY. And similarly, we can write VBR is equal to ER plus, so here it is minus ER, right? So here we can write EB plus minus ER. So this is the line voltage and this one is your phase voltages. So with the help of these equations, we can derive for balanced condition, we can derive various equations of line voltage and phase voltages. Yes or no? Okay. Now let us see various angles. Which are the angles? We know that this is the phase voltage, this is the phase voltage, and this is the phase voltage. So 120 degree, 120 degree, and 120 degree. Okay. Now let us look at this one here. If you look at this 90 degree here, so this is a 90 degree X and Y. Okay. Now out of this 90 degree, if we have an angle 120 degree, so can we consider this is a 30, 30 and 30 each? So here for balanced load condition, the angle between your extended, because here see how it is. Suppose this is a extended version here. This is an extended version. Fine. So here it will be 30, here it will be 30, here it will be 30, 30. So 30, 30, 30 each for balanced load condition. And hence we can write the various equations accordingly. Clear? Agreed? Agreed?
Yes, sir.
So here, if we want to write an equation of VL or VYB, can we write like this? EY plus minus EB. Or if it is a 30 degree here, can we write an expression for that? Yes or no? So if we write VRY, first equation VRY, then it is VR minus VY. Clear? So this is an expression we can write for this also. And here we can, because VR and VY are similar kind of things. And if we resolve it on this, so again it is multiplying by cos 30. Fine. So here in this equation, if we enter the values, fine, values of this VR, VY and resolve it onto Y axis, or what we can say your line voltage axis. So here we can have EPH and EPH. Fine. So we can write this with this into EPH into cos 30 degree. Agreed? We can write, because this is the vector sum of these two, and we can write this. If cos minus 30 will be cos 30. Agreed? And hence we can write this, because here it is to be written like this, minus VY and plus. So we can write this 2 EPH into cos 30, and 2 EPH into cos 30, that is nothing but cos 30 into root 3 by 2. Sorry, EPH into root 3 by 2. And VRY is your line voltage. So VL is equal to root 3 into VPH or EPH. Clear? So we can derive it from this diagram. Agreed?
Any question here?
Okay, fine.
Yes,
So,
sir.
so this way we can derive the line voltage as well as phase voltage equation. So VL is equal to root 3 times VPH, where phase voltage and this is line voltage. Okay. Similarly, we can derive the equation of current, but in star connection, the same current is flowing. So there is no need to flow, no need to write any equation for current or star connection. Okay. So we know that IL is equal to IPH for this star connection. Okay. Similarly, we can have a delta connection. And for delta connection also, we can identify the equation between line voltage and phase voltage. So for star, we know that. Now for delta, we also know that this VRY, VBR and VYB are line voltages. Line voltages, clear. And similarly, this IR, IB and IY are phase current, because here phase voltage and phase current are same. Here there is a phase voltage VPH, fine. So this phase voltage which is across this supply, so whatever the voltage that is a supply voltage, similar voltage will be available at phase also. So here in this case VL is equal to VPH or EL is equal to EPH, fine, for delta connection. What is the difference here? Difference in current here, because this current if rotates in this way, sorry, the direction is shown here this way, right? So here there is a difference of two different currents. So line current will be different from this phase current, and hence we can have various equations or relationship between line voltage and phase, sorry, line current and phase current. Clear? How does similar way we can draw the waveform for delta connection also. So this is a delta connection. Clear? And according to that, this is a VRY. Fine. Similarly, this is VYB and VBR. These are the line voltages which are at 120 degree each, 120 degree each, and here it is also 120 degree. Okay. So 120 degree apart, all these three vectors are placed that are the line voltages. Fine. Why we are considering here line voltages? Because now we know that from this line voltage there is a phase difference of current, IR. So this is our main part of this vector diagram. Similarly, here it is EY and here it is so students, just a minute. I'm just coming back within 2 minutes, right? Okay, students. So here in this case also, we can have three different currents which are in lagging position or lags behind the line voltage by 90 degree, or if it is inductive circuit, but we consider it is not inductive, it is a mixture of RL combinations, then it will be a phi curve. So this is a phi, VRY, VYB and VBR. Right? So here in this case, we can also extend these different vectors in the opposite direction. So this IB is extended equal to and in opposite direction with minus IB. Fine. So minus IB into IR, or sorry, minus IB plus IR. That is your resultant one. And this resultant one is what? Your line current. Line current. Fine. So this is a line current. current flowing through the line is line current. This is a phase current IR, and this is a phase current. So in line R, the line current is nothing but it is an addition of two different currents flowing through that junction. So this is a junction. So IB is flowing, IR is also flowing, but the direction, because it is out from this junction and it is into the junction as the current flowing in this direction. Fine. So here we can write IR minus IB. And similarly, we can represent the same thing here in this phasor diagram also. So this is IR and this is IB and this is IY. So we can extend this IB into opposite direction with equal magnitude. Then the resultant of these two, according to the law of parallelogram, we can find it. And this is the difference IR minus IB, and this is your line current, IL, line current. Getting me? Getting me, all of you? Okay, fine. So here also we can write an expression of IL. So IL is, or you can write IR minus IB also, is equal to IR plus minus IB. And similarly, you can write it for this one, this case also, and similarly for this case also. Agreed? Okay. Now, can we write an expression again? Because again, there are different angles, because this is 30, this is 30, this is 30, all 30-degree angles are there, fine. And if we consider the magnitude are equal, fine, considering balanced load, fine, we can write 2 times into IPH into cos 30. So in one case it would be cos minus 30, and in one case it would be cos plus 30. Fine. So cos minus 30 will be again cos 30. And again, we are going to have the equation that is cos 30 is root 3 by 2. So root 3 times IPH. So this is the relation of current IN and IPH in both the cases. Is that clear? Okay. Now based on this, we have different equations or different examples based on these different equations that can be written. Okay. So would be better if we consider all these examples by tomorrow morning. Now today I am going to start with another theory, that is measurement of power by 2 wattmeter method. Measurement of power by 2 wattmeter method. I hope all of you have studied this in your experiment called power measurement by 2 wattmeter method. Right? Okay. Yes. Anyone? Anyone? Any question? Our next theory is measurement of power by 2 wattmeter method. Is there any doubt between this line voltage and line current? Phase voltage and phase current calculations? Okay, fine. So all are agreed. I hope all of you understood it clearly. Right? So measurement of power by 2 wattmeter method. And similarly, in 3 different lines, R, Y, and B. By connecting 3 different watt meters, we can also measure. This is W1, W2, and W3. So looking at this circuit diagram, so consider this is a star connection or resistive star connected resistive load, or maybe inductive. Now we can measure the power with the help of 3 different wattmeters also. So there are 3 different methods. Method 1 is power measured by 1 wattmeter method, by 2 wattmeter, and third one is by 3 watt meter. Okay. Now let us come first of all by 1 watt meter method. Suppose if you connect 1 watt meter, either of any of these 3 lines, we can measure the power of one line, and if we multiply it by 3, we can get the total power consumed by these 3. Very simple. But in certain cases, this method would not be feasible, would not be because if the load is not balanced, if the load is not balanced, the star is not balanced, or these 3 different having a different amount of current flowing through it, then this method would not be okay for balance. Right? So let us consider 3 watt meter. So if we consider 3 watt meter, we can measure the power for unbalancing conditions also. Clear? And by adding the reading of W1, W2, and W3, we can have 3 watt meter reading. By adding all these 3, we can have the total power consumed by this 3 watt meter. Clear? So first of all, let us try to understand the equation of power. What is the equation of power here? The equation of power is P, that is active power. And this active power can be written with phase voltages by multiplying 3, because each phase consume a power. So another phase consume power. So here we can have 3 times VPH into IPH into cos phi. So this is equation of power for active. Yeah, because this is, if you consider this is a single phase, fine. Then we know that the equation is VI cos phi. So we consider this is a phi. This is considered VPH. This is also considered as VPH. And by multiplying with 3, we can have this equation VPH IPH into cos phi. And similarly, we can also write an equations for star connection and also for delta connection. We know that for star connection, VL is equal to 3 VPH and IL is equal to VPH. And for delta connection, it is VL is equal to VPH and IL is equal to 3 IPH. Okay. Now, if you want to write this power equation in the form of line parameters, because whenever you solve any examples, the parameters given in the form of current and voltages are always line voltage. Please remember, whenever you solve any numerical or whenever there is a practical existence of always there would be values given, and that values are line voltages and line current. Right? So if you want to write this equation of power, P is equal to 3 times VPH into IPH into cos phi into line parameter. Then simply we need to replace this VPH because IL is equal to IPH. So we can write IL here cos phi. Okay. So we can write this VPH is VL by root 3. So here 3 into VL by root 3 can be written. And if you solve this, it will be root 3 times VL into IL into cos phi. So whenever you write an expression of power, that would be always with root 3, and if it is given with the phase voltages and phase current, then it would be 3 times. So this is an expression for star connection. Now similarly, we can have the equation for delta connection. So P is equal to 3 times VPH into IPH into cos phi. Now this VPH will be equal to VL. So we can write 3 into VL into, now IPH is what? IL by root 3. So if you write IL by root 3 into cos phi, then you will get the similar equation from this. 3 by root 3 is again root 3. So we can write the expression P is equal to root 3 times VLIL cos phi.
Yes.
Is okay. So the equation of power either connected in star or in delta would be same. So root 3 VLIL cos phi, root 3 VLIL.
So this one also equation.
Is this okay?
Yeah.
Any doubt? Any doubt? Fine. Okay. So here we can have 2 wattmeter method, we can have 3 wattmeter method, but mostly 3 wattmeter methods are not used because of complex connections of voltmeter and wattmeter. Right? So wattmeter connections are, we all are familiar with the connections. I may repeat. Suppose if this is your coil, 2 different coils are there, fine, and 4 terminals are there, M, L, C, and V. And suppose if a kind of wattmeter, if you look at in the laboratory, right? So there would be an indicator which showing you the reading of 0 to 1500 watts, say for example. So here there are 4 terminals are given, fine, which are for C. So you can connect this C either in parallel or in series, right? Okay. So one more terminal that is called M terminal here, M terminal. So you can connect this to the main supply. So main supply input is given to this terminal. Phase I'm talking about, right? So connected to M terminal here. Then L stands for connected to the load. So here load would be there. Fine. So this is the connection of what we. So here one more terminal called L is also there. And here the fourth one, that is V. V is having 2 different ranges of 150 volt, 300 volt, and 600 volt according to the requirement. Fine. So C is a common for these 2 different pressure coil as well as current coil. So this is a current coil, this is a pressure coil, and we need to short it externally because it is not connected internally. Okay. So here with the help of this, maybe having 2 different types of current ranging, 10 ampere or 5 ampere. So if you connect in these 4 terminals, I can, if you connect it in series, then it would be 5 ampere. If it is connected in parallel, that would be of 10 ampere range. Okay. And similarly, according to the voltage, suppose if you measure 3-phase power, we know that the measurement of 3-phase power is 440 volts. Okay. So voltage range is 440 volts. So we need to choose this 600 volt for this range. Okay. Okay. So based on this, there is a multiplying factor. Multiplying factor which you need to be found. I hope all of you have understood what do you mean by a multiplier of a wattmeter and how does it work. Do you need to understand again? Anyone? Anyone would like to understand? Okay. So here, suppose if you consider 600 volt and if you consider 5 ampere current range, so 600 into 5, that is 3000. Now here the dial is of 1500 maximum, or suppose if you consider 3 at 3005, so the reading is 0 to 3000 range. Right? So here 3000 divided by this 3000, then it would be 1. So your multiplier is 1 here. Now if you consider 600 volt range for the voltmeter, and if you select the current 10 ampere range, then the rating of this wattmeter would be 6000. And this 6,000, now here we can measure up to 3,000 only. So if it is divided by 3,000, then we can have a 2. So multiplier is 2. So whatever the reading that you measure on wattmeter, suppose if you measure 1,000 in this case, in which case? In the second case, then this 1,000 would become 2,000, not 1,000, because multiplying factor is 2. I hope all of you understood this very clearly. Okay. Now in two wattmeter method, either of these three different lines, this wattmeter is connected like this. Fine. Sometimes, so this is, it's better if I use the different colors for this diagram. Okay. So this is R phase. This is Y phase and this is B phase. Okay. So various coils are connected like this is the pressure coil of wattmeter 1. And similarly, here or if you consider it from here also. So this is the coil. Now here, sorry. So here it may be connected either in star or in delta. This is delta like this. Okay. So here two different wattmeters are connected either in any of these three lines. Like suppose if it is R, Y, and B. Right. So this is M, L, C, and B. So the voltage terminal which is connected to the phase where the wattmeter is not connected. Right? And similarly here it is M, L, C, and B. So this voltmeter terminal which is connected to the third phase which is available in system. Right? So this is your wattmeter 1, W1, and this is wattmeter W2. Now here the theory proves that if we add this W1 and W2, we can measure the total power of this circuit in a three-phase system. So by adding these two, we can also have such kind of wattmeter, measurement of power by 2 watt. Let us prove that why W1 plus W2 is given you this way. Clear? So there is a theory based on various waveform where we can prove that with the help of phasor diagram that this W1 plus W2 that gives you total power of three-phase circuit. Clear? So we can have a diagram because here we considered only two watt R, Y, and B, where R and B, R, Y, and B, where R and B, where the two wattmeters are connected, and the Y is to be considered as return phase. Clear? So we can have the addition of the vectors of various vectors. Suppose if we consider, now let us draw that vector diagram. So this is VRN. Yeah, this is the phase voltage. Similarly, at 120 degree, that is VBN, and at 120 degree it is VYM. What does it mean? R and N. So it is a voltage between line and neutral. Fine. So neutral is a star point here. So this is the phase voltage. This is also phase voltage. This is also phase voltage. Now if we connect R, Y, and B, if we connect R and B, then we will consider this R and B only. Fine. So here, if we extend this vector into opposite direction, then this is minus B, Y, N. Agreed? And similarly, we can have this vector if you extend in the negative direction, then we can have this. So here the resultant one is this resultant one is your line voltage. Clear? And we can write this is VRY. So this is R, this is Y. So we can write this is VR. And similarly, this is minus VRN. And if we extend this one, and if we write like this, then this would be VBR, VBR or VB. Fine. And similarly, we can write it for VYB also. Clear? So here, instead of placing this diagram here, can we place it again at this way? So I'm just rearranging all these terms. Sorry, this one is the black one. So this is VBN, VBN. Yeah. Now this is VYN, and if we draw the resultant of these two, then can we have another vector here that is VBY? This is B and this is Y. So VBY. Yeah. So similarly, we can also draw for the third also, fine. But we have not made it for all three because we have connected two wattmeters in two different phases. So VRY is your line voltage. This is also line voltage. Yeah. So here W1, which will measure the voltage VRY because it is connected in between R and Y. मैंने आगे भी आपको बताया कि VAR ये Y आपका जो है उस दोनों के बीच में हमने एक W1 लगाया and RY and B. So this is B. So ये वोल्टेज जो यहाँ इस दोनों के बीच में लगाया that is W2. So W1 can be written as VRY. And what is VRY? Sorry, that is VRN plus minus VYN. Agreed? And we know that VRY and IR having some angle. Okay, so we can have a current vector also in this case. Suppose if this is VRN, and if we have the current for inductive load, so this is the current, or we can say IR current. Clear? Then there is an angle phi. Now, what is an angle here? We already discussed about that. This is an angle 30. So this is the line voltage. This is the line current. So total voltage, total angle is what between these two? That is 30 plus 5. 30 plus 5. Agreed? So here the angle would be of line voltage and line current would be 30 plus 5. And according to that, we can write these equations with VRY into IR into cos 30 plus 5. Because this is line current, and cos 35 is the angle between these two. And VYN is your phase voltage. Clear? So this way we can write the equation of W1, which is missing. So W1 will measure the power. W1 will measure the power. VRY is the line voltage, so we can write VL. IR is IL, line current, into cos 30 plus 5. And similarly, if we derived it for this case, then this is your VYB, fine, and current would be here. So here total angle is 30, this angle is 5. So 30 minus 5 would be there for wattmeter W2. So W2 can be written as VL into IL into cos 30 minus 4. Agreed? Equation 1 and equation 2. Now, from this vector diagram, we can write equation of W1 and W2. And these two different equations, if we add, then we can find the total power W, W1 plus W2, where we can write VL into IL into cos 30 plus 5, and another equation is VL into IL into cos 30 minus 5. And if we solve this, we can have VL IL cos 30 plus 5 plus cos 30 minus 5. And if we solve this C plus C, if we solve this C plus C, then we can have the equation looking like this: VLIL. Now, what is an equation here? Cos 30 into cos 5 here, minus sin 30 into sin 5. Clear? And what about this? This one plus cos 30 into cos 5. Minus minus would become plus now. So here cos. So plus here instead of minus, it would be plus here. So plus cos 30 into, sorry, sin. It would be sin 30 into sin. Okay. So we can solve this cos A plus B and cos A minus B, cos A plus B and cos A minus B, and we can write accordingly, right? So here two terms are going to be subtract from each other, that is sine terms, okay? And we can write is 2 times VL into IL into cos 30 into cos 5. Agreed? And we can write this cos 30 is root 3 by 2 into VLIL into cos. So if 2 is cancelled, then root 3 times VLIL. So this is your total power measurement of W is root 3 VLIL cos 5. That is a power equation where VL and IL are in line parameters. So root 3 times VLIL cos 5. Okay. So this way we can prove it that by 2-meter method also we can measure the power. Either it is connected in delta or either it is connected in star. Clear, everyone? So this is the measurement of power by 2-meter method. Any question if you have? We can discuss, otherwise we will meet tomorrow at 9:30 in the morning. Tomorrow is a Saturday, right? So all of you, please be ready with, because I'll little bit go fast forward for your solution of different numericals. Clear? Okay. Till then, have a good day. Any question?